In this video, we will introduce the analysis of variance, or ANOVA as it is usually called. Analysis of variance concerns comparisons of means among more than two groups. And it is possible to compare across more than one factor. A factor in the analysis of variance refers to an independent variable. So each independent categorical variable is called a factor, and we can have more than one independent variable at the same time affecting the same dependent variable. In this way, we can also study interactions, that is, whether the effects of one independent variable are constant or are themselves affected by the other independent variables. In this video, we will only consider the simplest case of the one-way analysis of variance that has to do with the comparisons of means among two or more levels, so two or more groups. Multiple factors and interactions will be discussed in another video. I would also like to note that analysis of variance can get very complicated very quickly. So we are not going to go into any depth. I only want to illustrate the main concepts here so that you will be able to run the analysis of variance in Jamovi and interpret the output. I do not recommend that you start going into the details of actually calculating it. We do not have time to go through this in this course. To see how the analysis of variance works, it is probably simplest if we start by comparing to the Ttest. So the Ttest is a way to test statistically a difference between two group means. This is the situation where you have a dependent variable that is numerical or quantitative, and you have an independent variable that is categorical or qualitative, and this categorical independent variable has only two levels, so takes only two values. In this way, two groups are formed. So the relationship between a categorical independent variable and a numerical dependent variable is tested by asking whether the two means are different. The means of the two groups, are they the same or different? Now, this is only possible by definition with just two groups, because the Ttest works by calculating the standardized difference between these two groups, the difference in terms of how many pooled standard errors. So it is not possible to run a Ttest if there are more than two groups. What if we do have more than two groups? What if it's not just boys and girls, but three different grades or three different interventions? Well, then there are more differences. Which of the group differences should we compare to find out if our two variables are related? The answer is we don't need to calculate any group differences if we think of the relationship question in a different way. Instead of addressing the group means directly in terms of their differences, we think about the variance of the data, so the dispersion in our data values, and how much we gain by considering different sets of means. We'll see now how that actually works. The important concept that is also in the title of this analysis is variance. Variance is a measure of dispersion for a variable, and as you will remember, it is the square of the standard deviation. Actually, it is the thing that we calculate when we calculate the standard deviation right before we take the square root. That's why it's the square. So this thing is the squared standard deviation of the sample. And the important quantity that we're very interested in here is this part, which is called a sum of squares, because it is a sum of squares. It is the sum of squared deviations from the mean. So we subtract the mean from each data point, and this difference is multiplied by itself, and all of these are summed up. So this is the total squared deviation that is then divided, and then the square root is used to calculate the standard deviation. But for now, let's just focus on this sum of squares. And to see how we work with this sum of squares, we're going to use an actual example, and we will go with the simplest possible example, which is just two groups. Just for showing the calculation, we're going to use only two groups, and we'll use the example of receptive vocabulary scores measured for two groups of children. And we're asking, do girls and boys in kindergarten differ in receptive vocabulary? This is a sample of 15 girls and 15 boys. These very small samples are only good for examples in the statistics course. They're too small for actual research, but they're good enough for illustration. So for this sample, we have a mean raw score of 60.7 for the girls and 67.9 for the boys. And the corresponding standard deviations are 10.3 and 12. And the question is, are these findings consistent with sampling from a single distribution? Or do we need to conclude that the populations of girls and boys have different means? Let's see how the sums of squares helps us reformulate this question. Here I have indicated each score by each child with a circle. So these are all the children from both groups together, 30 data points along this axis of vocabulary. And the grand mean, the overall mean is called grand mean of all these 30 values is right here. This is the mean of all these points. It's 64.3 is the mean raw score in receptive vocabulary. And the distances of the actual data points from the mean, if you recall, are called the deviations and are these lines. So this line here, the first line here, represents the distance of the lowest data point from the mean. And then the next line represents the distance of the next data point from the mean, and so on. So these lines are the distances or the differences of each data point from the mean, and they are these quantities here. So if we use the lengths of these lines to multiply each one by itself and then add up all of the results, that would be the total sum of squares. Let us think a little bit about what this means. One useful way to think about this is as the total deviation. Actually, it is not correct to think about this as a sum of distances because there is a square going on. So the correct way to formulate it is that we use each line to form a square with side equal to the line. And then we put all the squares together, and the total area is the total sum of squares. This would be the correct thing to say. However, it is difficult to visualize sums of areas. So you can roughly think of it in the incorrect but useful way of imagining all of these lines one after the other, forming a very long line. That would be the total deviation. This is incorrect technically, but is still useful because you can more easily imagine all of these lines put together to form one long line that would represent how far from the mean our data points are. So that would be the total deviation. Let us now see the effect of grouping. Our independent variable is sex, and that variable splits our data points into two groups. So we have the girls and we have the boys, indicated here by two different colors. And the respective means are here. The mean for the girls is lower than the mean for the boys in this sample. So if we have the group means, we can very easily calculate the deviations from those means instead. Here are the corresponding lines. So the distances from the mean are an index of how far off you will be if you were to predict each data point by its mean. These are the deviation lines. So for this data point now, the deviation line is this one. For this data point, it's this one. For this data point, which is a boy's point, it is this one, and so on. So we get a different reference for each group. Instead of subtracting the grand mean from every data point, we subtract the mean of the corresponding group. And so these are called the group 1 sum of squares, or the female sum of squares for the example, and the male sum of squares. We have two sets of sum of squares, but they're all of the same kind because in each case, we subtract the mean of the respective group before we multiply that by itself. And we can add all these up, that these and these would be the new set of sum of squares, so the new total deviation in terms of sum of squares. Let us see how this compares to what we had before. If the two groups had equal means, so if the mean for boys were here and the mean for girls were here, then using the two means would make no difference in how long these lines would be. They would run to the same point. But now they aren't equal. So the boys' mean is a bit to the right of the grand mean. The girls' mean is a bit to the left of the grand mean. This means that each group mean now is a bit closer on average to the group data points than the grand mean was. So this data point has now a group deviation that is this long. This is shorter than the deviation it had from the grand mean. And this point's deviation here is shorter than its deviation from the grand mean. And so on for most points. This is not true for this point. So the new deviation here is actually longer than its corresponding deviation from the grand mean. But for most points, because the points for the girls are a bit to the left on average, these sums of squares will be less than the sum of squares if we were using the grand mean. And if we do this for both groups together, we see that on average, these lines will be a bit shorter than these lines. So this is the deviation that we gain. We reduce the distance of each data point by its predictor. What is the predictor? Predictor is our model for the data. If our model for the data is the grand mean, and we know nothing else, then if anyone asks us about a group's vocabulary, we have to guess that it is the grand mean. If the variable sex is related to vocabulary and we're asked about a child's vocabulary and we are told their sex, then we should change our guess. We should provide the boys or the girls mean depending on the sex of the specific child, because this will improve our guess. It will help us make a better prediction closer to the actual value on average if the variables are indeed related. So if the variables are related and these two means are not equal, these lines, which correspond to their deviations, and then the squared lines would be shorter or smaller in area, respectively, from these lines and the corresponding squares. We are using the distance between the means, which is how much the two groups differ, to improve our prediction and to reduce our error, to reduce how far off we will be when trying to predict the dependent variable. The final thing to note is that for each data point, the difference between the original deviation from the grand mean and the new deviation from the corresponding mean, so how much shorter this line is from this line, the difference is the difference between the group mean and the grand mean. Just take a moment to think about this. This line is longer than this line, and the difference in how long they are is exactly equal to the difference between this mean and this grand mean. So this line is as long as up to here, which is the position of the group mean, and then the difference between the group mean and the grand mean is how much we have shortened the line by using the group mean. So the total length of the original line is split into two components. It's split into a difference between the grand mean and the group mean, and the difference between the data point and its own group mean. We can think of the difference between the means as the portion of variability in the data that is accounted for by the grouping. So how much of the total variability in our data is actually accounted for by taking the independent variable into consideration? That's how much. This average distance is the distance between a boy and a girl on average. The rest of the deviation is not accounted for. That is individual variability. So individual children differ not only from the grand mean, they also differ from their own group means, and that's the part that is not accounted for by their sex. It's accounted for by other factors. Let's see how this works out if we add things up. Focusing on the sums of squares, one very important thing is the sum of squares within, which is the sum of the square distances from the group mean for both groups summed together. So the red and blue lines squared and added together, these are the square deviations for all the data points with reference to their own group mean, and that's called sums of squares within, because it is calculated within each group. So each group is using its own mean to calculate this. This is the sum of squares within. And this is contrasted with the total sum of squares, which is calculated by subtracting the grand mean from every data point and then squaring that. So this is the total sum of squares. And as you may have imagined, the difference between these two, the sum of squares based on the grand mean, minus the sum of squares within, is called sum of squares between the two groups, and is actually calculated by summing the squared distances between the group means and the grand mean, the other group mean, and the grand mean. So these differences as many times as there are data points. But it's still equal to this difference. So in a way, what we've done here is we have a total sum of squares. The total sum of squares is the total square deviation of all the data points from the grand mean. And this is a measure of variability in our data. It is not standardized or normalized, and it's not per data point like the variance. It's just total variability. Each extra data point adds variability, adds to this number. So if we have lots of data points, we will have a larger sum of squares. So that's the total variability in our data that we want to account for. And that total variability is split into parts. One part of the variability is the part that is accounted for by the grouping. So that's given by the difference between the group means and the grand mean. If the group means are equal to the grand mean, then no variability is accounted for by the grouping. The grouping makes no difference, the variables are unrelated. But if the grouping does make a difference, then we can account for some of the variability in the data by grouping them. And then the differences between the group means and the grand means are the variability between groups. So this is the sum of square between groups, and that's the part that we actually account for by the grouping. And the other part of the total sum of squares is the within, which is what's left over. So the deviations of the data points from the corresponding group means for both groups together. And these things add up. So this sum of squares, if you calculate and add these up, plus this sum of squares, if you calculate and add these up, plus these, are equal to this sum of squares. So our total variability is split between groups variability and within groups variability. And this is the core concept of the analysis of variance. Because what we're interested in is how big the variability is that we can account for compared to the variability that we do not account for by the grouping. Before we actually calculate that, we need to know the degrees of freedom that are associated with each sum of squares. The degrees of freedom for the within sum of squares are equal to the number of data points for one group plus number of data points for the other group minus 2. Why minus 2? Because this sum of squares has two means. We calculated a mean for each group. So each mean removes a degree of freedom because it imposes a constraint through the sum. So if there are two means, we have to subtract 2 from the total number of data points. If we had more groups, then we would have to subtract more here. As many groups as we have, we subtract 1 degree of freedom from the number of data points for each mean calculated, that is, for each group. For the total sum of squares, the degrees of freedom are the number of data points together minus 1, because this requires the calculation of only one mean, the grand mean. And the difference between these two is the number of degrees of freedom for the between groups calculation. So the sum of squares between has 1 degree of freedom. And that you can think of as the difference between the total degrees of freedom and the within. The number of degrees of freedom cannot exceed the total. So we split the degrees of freedom, as we also split the sum of squares, into within and between. So this is one way to think about it. Another way to think about it is through the way it is calculated. The sum of squares between can be calculated by subtracting a modeled data point for each value, which is its own group mean, from the grand mean. So the actual mean that is relevant here is the mean of the two means. So one mean is actually used for this calculation. So there are two data values, and one mean their mean that is used for the calculation. So that's 2 minus 1 is 1 degree of freedom. If we had more groups, the number of degrees of freedom for the between sum of squares would be the number of groups minus 1. And now we are ready to calculate the ratio that is of interest, which is a ratio between mean sums of squares. The ratio that we're interested in has two components. The first component on the numerator is called the mean squares between. It is the sum of squares between divided by the degrees of freedom between. So this is the measure of variability that is accounted for by the grouping. You can imagine here the lines joining the group means to the grand mean, but one line for each data point, divided not by how many data points we have, but by how many degrees of freedom there are. So one less than the number of groups. So this is how much variability is accounted for by the grouping. And in the denominator, we have what is called the mean squares within, or the residual mean squares, which is the sum of squares within the group. So each data point from its own group mean, squared and summed, divided by the degrees of freedom within. So this is the number of data points minus the number of groups. And this is an index of the variability in the data that is left over. It's not accounted for by grouping. We group the data, we reduce the deviations, but there's still deviation. Each data point is not equal to its group mean. So this is the leftover part. Leftover in statistics is called residual. So this is also called the residual mean squares. And this ratio then is the ratio of the part of the variability that the grouping accounts for divided by the part of the variability that the grouping doesn't account for. And importantly, remember that this plus this is the total variability of the data. So the sum of squares between plus the sum of squares within is all the sum of squares we have in total in our data. Now, just putting in the numbers, we come up with the number 3.1. This is called the F ratio for this comparison, and is an expression of a ratio of sum of squares. So it's an expression of a proportion of variability that is accounted for. This is the very simplest possible case. It's called one-way ANOVA because it has only one independent variable and it has only two groups, two independent samples. So it's easier to see. But note that there was nothing special about having two groups. Nothing in these calculations limits us to having two groups. We could have had more groups and have done exactly the same thing. Each point subtracting its own group mean and so on. So this generalizes immediately to more groups. Importantly, because this is a two-group situation, we could also have run a Ttest. You know how to do this. So the distance between the two means standardized by the pool standard error and the t-value for this would have been 1.76. It is no coincidence that if you multiply this by itself, you find this value. So for a two-group one-way ANOVA, in which both the F and the T statistics can be computed, it is the case that the F is equal to T squared, which makes a lot of sense because there are two tests that are answering the same question. Are the means statistically significantly different? But they're answering it from a slightly different point of view in terms of how you calculate the relevant statistic. But they are, in fact, mathematically equivalent. To get a p-value for our F statistic, we need to look it up in the Pvalue app or in table, or ask the computer to produce the value for us. So in this app, we can select the F distribution, enter the 2 degrees of freedom, first in the numerator and then in the denominator, enter the value of the statistic. This is our F, and then we obtain the p-value. It is no coincidence that this is equal to the p-value we would have gotten from the t-test in this situation. Note, however, that the sampling distribution for F is very different. This is the curve of the F sampling distribution for 1 and 28 degrees of freedom, and it's always positive. F is always positive because F is a ratio of sums of squares, essentially. So divided by degrees of freedom, but there's sum of squares, and sums of squares are positive because squares are always positive. So you cannot have a negative sum of squares. And if grouping doesn't account for any variability in the data, then the F ratio will be very small. So the sum of squares between will be very small, will tend to 0 if you account for nothing by grouping. But if the grouping is useful, if the two variables are related, in other words, then F will be large. The more the two variables are related, the larger the F will get. And so the smaller the p-value. Ftests are typically reported using a special table. The table looks like this. There is a line for each variable and a line for the corresponding residual. So here we have, in this row is the sex variable, and in this row is the residual. The sex variables are grouping variable, has 1 degree of freedom, so because there's 2 groups. This is the sum of squares between, the mean squares between, which is the sum divided by the degrees of freedom. And for the residual, which is the within case in our example, we have 28 degrees of freedom because the 30 data points involve 2 means, 2 groups. The sum of squares within, the mean squares within, which is the sum divided by the degrees of freedom, and then the F statistic for this test, which is given by dividing this mean square value by this mean square value. The F statistic is then combined with the degrees of freedom to look up the p-value. And the way this is actually reported in text is this one. So you report F, the 2 degrees of freedom, the value of the F statistic, the p-value with 3 decimal places and no leading 0, and it has recently become necessary to also report the mean squares between. So the mean squares associated with this factor. This is the result of the statistical test testing the hypothesis that the 2 means are not equal, and the p-value is greater than the conventional reference level, the conventional alpha of 0.05. Therefore, we cannot reject the null hypothesis that the two means are equal, and we cannot conclude from these data that girls and boys have different vocabulary scores at this age. What about the effect size? As we've said before, the statistical hypothesis test concerns whether we detect a relationship, but it doesn't tell us how strong this relationship is. What would effect size be in the context of the analysis of variance? If you think of the Ttest, where we could only have two groups, so two levels, the Ttest focuses on standardized differences between means. Standardized in terms of standard error gives us the t-value, and standardized in terms of pooled standard deviation gives us the d-value, which was the effect size. So the effect size in the Ttest was how many pooled standard deviations away are the two means. In the ANOVA, we do not focus on the group means, on their values themselves and their differences. Instead, we are concerned with the sums of squares, which are indices of variation in the data in comparison to the means. So they're indices that have to do with how far the data values are from the means. And the statistical test is a ratio of sum of squares accounted for over sum of squares not accounted for. And each one is related to the corresponding degrees of freedom in the test, which means that, of course, the statistical hypothesis testing depends on sample size. Greater sample size allows us to discern smaller differences. That's how the degrees of freedom function in the F ratio. The effect size doesn't have to do with the sample size. The effect size is how strongly are the two variables related in our sample, or how much we can predict one from the other. That's a different question. And in the context of the analysis of variance, the effect size is the proportion of the sum of squares that can be accounted for by the grouping. It's not whether this is statistically significant. It's not whether we can conclude that there is a relationship, but it is how much is this relationship? How big a proportion of the total sum of squares can we account for by grouping? How much do we reduce the uncertainty in our data by grouping them? And this is called the eta square. If we go back to our ANOVA table and we see that dividing this number by this number gives us the F value for the statistical hypothesis testing, indicated here, this is the F part, but the effect size is given directly by the sum of squares. Remember that this plus this is the total sum of squares. Between plus within equals total. This is how we have split the deviation observed in our data. We split it into a group-related part and a group unrelated part, which is the within. So the measure of effect size here, eta square, is given by the sum of squares between, this is the sum of squares accounted for by the grouping, divided over the total sum of squares. So the sum of these two. And that's 0.10. So we're talking about 10% of the total sum of squares in this data set is accounted for by grouping them into girls and boys. 10%. But because the samples are small, this 10% is not statistically significant. If we got 10% out of a much larger sample, it would certainly be statistically significant. How can we interpret this F ratio and the result of an analysis of variance more generally. One relatively abstract way to think about it is as answering the question whether it is worth giving up degrees of freedom for gaining variability in the data that we can account for. To give up degrees of freedom is associated with calculating more means. So if we group things, if we form more groups, instead of one total group have two conditions or two special groups or more groups, each group will have its own group mean. And by doing that, we take out degrees of freedom. Is it worth grouping when we consider how much of the total sum of squares we are gaining and how much is still left over unaccounted for? That's one way to think of what the analysis of variance is doing. And the way it's doing it is by comparing a squared deviation that has to do with the groups, so how far the groups are from the grand mean, and comparing that against the square deviation that we are not able to explain. So the square deviation of each data point from its own group mean, this ratio. If we think of it in terms of the null hypothesis is that the group means are equal. If the group means are equal, their difference from the grand mean will be 0, and so the sum of squares between will be 0. So for exactly equal group means, the sum of squares between will be 0, and so the F ratio will be 0, and that's the null hypothesis, that there is no difference. The alternative hypothesis then is that the group means are not equal. And this is something that we need to be careful with. That the group means are not equal is the same as saying that the two variables are related. If the independent variable is related to the dependent variable, then the group means will not be equal, because the independent variable will help us predict the dependent variable to some extent by using the different group means. So the alternative hypothesis is that the group means are not equal. This doesn't tell us anything about which group is larger than which other group. The statistical hypothesis testing is only telling us whether grouping is useful, whether grouping leads to a statistically significant difference, whether the two variables are related. In order to see how much they are related, we need the effect size. In order to see how they are related, which mean is greater than the other, we need to look at the mean values themselves or their graphical representation. So different questions, different aspects of the analysis that provide the answers. This is particularly important when you think about the number of groups, or in other words, the number of levels in the independent variable, which is a factor. As we said, the one-way analysis of variance can be performed in exactly the same way regardless of how many groups we have. So the independent variable can have many levels. We just go through the exact same calculation with the corresponding number of groups. The null hypothesis is always that all group means are equal, so there are no differences. No differences is the null hypothesis. All group means are equal to each other and to the grand mean. That's the null hypothesis. Thus, the alternative hypothesis is that not all group means are equal. if there's only two groups, the alternative hypothesis is that the two groups have different means. But if there are three or more groups, the alternative hypothesis that not all group means are equal doesn't tell us which means are different from which other means. If there are 10 groups and we get a statistically significant F ratio, we don't know which of the 10 means are different from which others. Maybe just the first mean is different from the second, and every other mean, so the remaining 8 means, are equal to the first mean. Maybe there are 2 or 3 or 10 differences between the means. That's not visible in the F ratio. So the statistically significant analysis of variance, the statistically significant F, can tell us if there are any significant differences, because the statistical hypothesis you're testing is whether the two variables are related, that is, whether we can reject the null that says that all means are equal. If we get a statistically significant F, and if we need to know which groups differ from which other groups, we have to follow up with more analyses. We have to actually compare individual pairs of groups or individual pairs of means. So these are called pairwise comparisons. And if we do them after running the ANOVA on the basis of the significant result, then they're called post hoc comparisons. So after the fact, after having seen the statistically significant result. And then we need to perform statistical correction for running multiple tests, because running multiple tests raises the probability of getting false positives. If we run one test that has an alpha level of 5%, then we have a 5% chance of a type 1 error. But if we run two tests, each with an alpha level of 0.05, then our total chance of a type 1 error isn't 5% anymore, because each of the comparison has a 5% chance of a type 1 error. So we must correct for the fact that there is more than one possibility of making this type of error, and that's called a correction for multiple comparisons. So the important take-home message from this is that the analysis of variance only tests the hypothesis that not all group means are equal. And for deciding how strong the relationship between the variables is, and for seeing what is actually different from what, we need different kinds of indices that we can calculate after running the ANOVA.